This is Wes Weimer here with the first in a series of video walkthroughs to help you get started on the programming assignments. Programming assignment 1, the Rosetta Stone, asks you to write topological sort in a few different programming languages. In this guide, we're going to consider similar graph algorithms, like Dijkstra's shortest path algorithm, and implement them in Python and OCaml together. And for Python, I'm going to focus on or include list comprehensions and the implicit edge list graph representation to give this a bit of a functional flavor, since we also cover functional programming in class. Well, let's get started. I'm going to be using Windows for these videos because it's typically the most commonly used operating system by students, but I'm using this Cygwin environment on top of it, which makes it look a bit more like Unix, and I recommend that for all students. So this should be fairly similar for students using Unix or Mac OS X. PL people are very bad at naming, and I'm no exception. If I have to do a shortest path exercise in Python, I will call it path.py. One of the first things I will do is make a little comment at the top listing my name and UVID just in case something goes wrong. And then I recommend starting off with a sort of a comment description to find the shortest path from a source node to dest in a graph. And then what you think the major steps are. For example, I think first we'll have to read in the input, read in the graph from the input. And I think we'll have succeeded if we can find the edges and the vertices. If we have both of those, then I feel like we really have the graph. And then step 2 will be to actually find the shortest path, which may be a little harder, but we'll get to that later. So step 1, read in the graph from the input. And what's this graph going to be like? We recall from the PA1 web page that if we had a graph like this, where A goes to B, which goes to C, we would write it down as A goes to B, and then B goes to C. And our input file would be just like this, but without the Python comment characters. But if we are interested in finding the shortest path, then these edges will probably have weights on them. Like say it costs 5 units to get from A to B, and maybe 3 units to get from B to C. So how should we represent that? Well, for the purposes of these videos, we'll just put it right between source node, weight or cost or distance, destination node. All right, so that's our plan. Regardless, in these exercises, we read in from standard input, sort of one thing on each line. So one of the first steps will be reading in a bunch of lines in Python from standard input. And I may have forgotten how to do that, so I'm going to try to take advantage of some course resources. I can go to, actually I see that's between EU and LDI. I'll go take a look at Programming Assignment 1, the Rosetta Stone, and since I've read through all of it, I recall this part in the middle where there were some resources available to us. PA1 hint provides concrete implementations in every language with this course. Oh, that sounds pretty handy. I'll just go find that, shell out here and download it, and then unzip it, and I see that one of these files is doing something in Python. So let's just pull up that Python file, reverse sort the lines from standard input, and we seem to do this import sys, and then lines is sys standard in read lines. Read every line from standard in. So we'll just get started with that. That seems pretty good. And one of the strong suggestions I will have for this course is to test after writing just a little bit of your code. So even though we should feel pretty safe because we got this code from the course webpage, it may not be doing what we expect, or we may not be using it correctly. So let's just say for every X in lines, I want to print out what I think the line is. All right? I want to test my program, even though it's just this small. And to test it, I'm going to need some sort of graph input. So let's make a very simple graph, and we'll just do this A goes to B goes to C thing that we were talking about in the comments. So I've got my simple graph, A5B, B3C. And now I want to run this Python program on that graph, Python path.py, and we're going to read input from simple graph. If you're not as familiar with Unix, this less than sign means take the contents of the file on the right and feed them as input to the process on the left. Unix is big on pipelines. Your operating systems class has more details. Now, this seems pretty good. We have sort of all of the information we were expecting, A5B, B3C, but if we look at it, we had really hoped that the left arrow and the right arrow would sort of line up, that this would be 6 lines long, and instead it's 12 lines long, and they don't line up at all. In fact, the right arrow is on the next line. So if we think about this for a bit, we might conclude that when we read in the input, we kept the new line character after A. There's trailing white space that we read in from the input, and we want to get rid of it. How do we get rid of it? Well, let's ask Google to find out. How to get rid of white space in Python. Remove all white space from a string, Stack Overflow, the source of all power and knowledge in the universe. Look, we're carrying out this video guide just as a student would program. We Google every few moments. It looks like there is a strip function that removes white space. Well, when learning about a new function like this, I like to try it out in the interpreter. Python, Ruby, OCaml, these are all languages that have sort of friendly interpreters. So let's say we have some string that says like hello, and then it's got this extra white space at the end. And they say there's a strip function we can call on it, and I want to know, is that going to destructively change the original string, or is it going to return a new string? It looks like it returns a new string, so I'll need to make sure that I do something like b is a.strip, print b, in order to get the results we're expecting. Now I could have some sort of for loop where I iterate over all of the lines and apply this strip function. But it might actually be more convenient to use Python's list comprehension syntax. In Python, you can have a list like 1, 2, 3, and suppose I wanted to multiply each of those by 2. So I have some new list. Well, it's kind of like I want to multiply every element x by 2 for every x in the original list. Voila. And this allows you to, this is sort of like a map function if you're familiar with MapReduce. You can also have a filter on the end. This will take every x in the original list, but only those that satisfy this predicate, only those that make x less than 3. So here, because 3 is not less than 3, it's equal to 3, we take the 1 and the 2 and we multiply those by 2. This is Python's list comprehension syntax. If I'm a little rusty with Python's list comprehension syntax, there are a number of guides I could go check out. So the lines I really want are strip x for x in lines. And now let's rerun our test. And now we get the 6-line output we were expecting. All right, that's very promising. But actually, I didn't really want 6 lines. All right? And now what I want to do is convert this sort of ABC into like a tuple ABC. I'd rather have it be 2 edges, each of which has 3 components. So I want to know, how do I convert Python list into tuples? Well, once again, I could try, maybe Google can help me out. Python, convert list into list of tuples. Convert list to a list of tuples. Python. Ho ho. This is the input list. 1 term, 3, 2. Oh, this is basically just what we have, except this person has, sort of 2 elements, like a weight and a node, and we have 3. How do we convert that easily in Python? The answer, we could use an iterator and then the magic zip function. You want to group 3 items at a time? Oh, you've read my mind, Stack Overflow. That is exactly what I want. We can use zip it. That sounds like an 80s commercial, and I would know. All right, well, let's just steal this code from Stack Overflow. We iterate over our list, which is lines. And then when we're done with this, we're going to have our edges. And once again, I want to test. I want to sort of print this out, right? So we'd have an A, a weight, and a B in edges. And we want to print the edge is A, weight, B. Let's see if we've found all of the edges correctly. Oh yeah, so we had 6 lines, which become 2 edges. Just what we'd hoped for. All right, we have the edges, and this is the implicit edge list graph representation that I was talking about. But let's say we also want the vertices. Well, for every one of these A weight B, I could just pull out the things in position A, right? And that might be a good approximation to the vertices. So the vertices could be every A for A weight B in edges. Right? That might work. So for every V in vertices, print vertex is V. Again, this is to sort of test every few lines just to make sure we don't compound a mistake. Let's see. We expect vertices to be A, B, and C. Uh-oh. We only got A and B. And if we take a look, that's because C only ever appears in the second destination position. It never appears on the left. And we could be smarter about this, or we could copy and paste code. Well, let's copy and paste code. All right. We'll do the same thing, but now also gather up B. So now we have the vertices we wanted, A, B, and C, but we've also got this extraneous B trailing around. And one way to think about this is that we're using sort of a list to implement a set. We really want the set of vertices, but right now we've got a list of everyone that appears. If I don't quite remember how to convert from a list to a set, how to convert a set to a list, turning the list into a set, how do we actually do it? Ah, there's a little set constructor. All right. So what if I just say, make me a set of vertices? Ah, now we have the 3 vertices we were expecting. All right, so this seems pretty good. So now in the grand scheme of things, it's time to actually find the shortest path. Okay. And in theory, we all, of course, have Dijkstra's algorithm memorized, but let's say I don't. I certainly do not. Dijkstra's algorithm. Let's see if Wikipedia can help us out. Oh, it can. Thank you, Jimmy Wales. We could read all of this text, but maybe there's some convenient pseudocode. Oh, convenient pseudocode, just what I wanted. So the first step, create the vertex set. I'm pretty sure we already have that. All right, they want to keep these mappings dist and prev. Let's just grab this for now. And they also want to add V to the set of all vertices, but we've already constructed the set of all vertices, right? Unvisited nodes. So let's just go back and implement this in Python. Oh, that copy and paste looks ugly. Let's use copy and paste mode. Oh, now it looks much prettier. So they want us for V in the set of vertices, distance V gets infinity, and previous V gets undefined. Well, actually, there are a number of undefined things going on here. Right? We want to declare what we think these variables are supposed to be. And I'm just going to use like a lot of 9s for infinity. You should probably think of some better way to do this. Maybe there's some sort of max int maneuver or an incomparable data type. But for the purposes of rapid testing, we'll just use a lot of 9s here. And undefined is the name of some vertex that would never actually occur, and I'll just use a question mark. And again, for our automated testing, you just know I have some evil test case where all the vertices are named like question mark and period and $ and that sort of thing. So you'd want to be a little smarter about this in a real implementation, but this will be fine for now. And then we've got these dist and prev maps, and just for slightly better style, we will make uninitialized dictionaries to hold those. So they say unknown dist from source to V, and previous node in optimal path from source. All right, and let's just try this again to make sure this code actually runs in Python. Do we get to the end? Ah, we got to the end. All right, no hideous syntax errors. So now let's take a look at the next bit of pseudocode. Again, we've already we have all of the nodes already. We did that earlier with list comprehensions. So now we want dist to source gets 0. And this little arrow doesn't actually occur. And for us, do we have a source and a dest? I guess our source is going to be node A. We'll just hard code that for now. High quality software engineering. All right. And now there's some sort of while loop. While Q is not empty. Well, what was Q? Q was their name for the set of vertices. All right. There's a better way to check for empty lists in Python, but we'll do it the ugly way. U gets the vertex in Q with the minimum distance. Set U to the vertex in Q with minimum distance U. How do we want to do that? Actually, there are a number of ways. We could try to do it functionally with list comprehensions, or we might just use some sort of for loop to walk down the list and find the smallest one, or we could sort the list and return the first entry or something like that. Since we've been very nice about sets and list comprehensions, let's do this part in a hacky manner. Let's just have a big for loop. So we're going to go over every candidate in the set of all vertices Q, and if the distance to this candidate is less than the min dist found so far, then our final answer U becomes this candidate, and the min dist found so far gets whatever the distance to this candidate is. And we just need to initialize that the best thing we found before we even start this is infinity and beyond. Buzz Lightyear would be proud. This is going to allow us to succeed at this strict less than comparison if that's ever necessary. All right. And then they say remove U from Q, which we'll get to later. Let's actually just test this right now. And we say, oh, what's the U that we found? And then this is in the middle of a for loop. Pull this back out just a little bit. We iterated over all of the candidates. We actually want to set this minimum distance before we iterate over all the candidates. If the distance to the candidate is less than the minimum distance found so far, this is now our best shot. We keep track of the best distance found so far. We print out the result. All right. What do we think the answer should be before we run our test? Well, we could get a little more information about that by actually printing out, we'll print it out down here, this distance mapping. They all start out at infinity, but then the distance for node A, our source, goes to 0. So if we're trying to find the minimum, I hope we find node A. Well, once again, here are the 6 lines we read in. That results in 2 edges. We enumerated all the vertices. Here's the distance mapping. A is 0, C and B are both infinity. And we found the minimum one, which is A. All right, that seems pretty promising. So then they say we want to remove U from Q. Maybe I don't remember how list removal works in Python, so we could try it out in the interpreter. If I have some list like 1, 2, 3, and I call a.remove, removing element 2, does that return a new list or destructively update the first one, or what's the deal? It looks like it destructively updates its receiver object. All right. So we can just say, remove it. All right. So now we want to go back to our pseudocode, and we're here for each neighbor v of U. All right, so there are a number of ways we could find these as well. We could do list comprehensions, or we could do some sort of for loop and just take a look at all of the edges. Let's try some sort of for loop. For every A weight B in the set of edges that we have available, right? If A is U, then we found the neighbor that we wanted. We found this neighbor V. All right. So U is a neighbor of V is a neighbor of U with length, distance, weight, W. All right. So they say do some math. Alt gets dist of U plus the length between U and V, which we just said for us is called W, the weight. All right. All right. And then there's some sort of little check here. If alt is less than the distance to V, a shorter path to V has been found, then distance to V gets alt and previous to V gets U. All right, that seems pretty good. Oh, and then they'd actually be done. But we want a simpler way to test it. We're just trying to find the shortest path from the source to a particular destination. I wonder if Wikipedia can help me out. If we're only interested in the shortest path between vertices, source, and target, oh, that's me, we can terminate the search after line 13, right? So right before we do this remove thing, if u is equal to the target. Okay, so if u is equal to the target, we found it. We win. Let's just see if that ever happens. We probably need target to be defined. So right now the target is C in our very simple graph. All right, let's run this and see if it ever works at all. Hopefully there are going to be some interesting bugs for us to track down. Ho-ho, an interesting bug for us to track down. File path.py line 73, unsupported operand types for plus, int, and stir. So here's the only plus on that line, distance u plus w, and they're saying that distance u is an int. Well, that's good. But w, the weight, is a stir. Why does Python think the edge weight is a string? Well, if you recall at the top, we read in all of the lines as strings and stripped all the white space from them, but we never actually converted the weight in the middle to an integer. Instead, it's as if we had like the string 5 here when we want the integer 5. So we'll just go down. We could either change this in the primary data structure definition, or it turns out that this is actually the only place we ever use them. We just convert it to an integer right here. Right? Edge weights are stored as strings. So now let's rerun it. Oh, we win. We visited A, B, and C, and we got there. But there's more than just saying we won. Like, we have to produce the actual path. So it says now we can read the shortest path from source to target by reverse iteration. Reverse iteration. That sounds much cooler than it actually is. Once again, we will just copy in this code, and we found it. Find path from source to target via reverse iteration. We'll use your highfalutin terminology, Wikipedia. All right, it says initialize S to the empty sequence. Done. Initialize U to target. Done. Although I'm pretty sure this line also guarantees that, but who am I to argue with the mighty Wikipedia? While preview is defined. What does that mean? Well, up here we had an undefined, so we can say if you're not undefined, then you're defined. Construct short path with stack S. Insert U at the beginning of S. There's like a good way to do this, and there's the ugly way that I will do. Ho ho! Push the vertex onto the stack. And then they say traverse from target to source. U gets preview. Traverse from target, my gosh, to source. And then finally, outside of the loop, once again, push source onto stack. So print shortest path is S 0. So let's run it again and see if we're getting the output we're expecting. The shortest path is ABC. Well, in our simple graph where there are only 2 edges, A goes to B and B goes to C, yes, that's correct. But this test case doesn't actually give me high confidence that we're correct. It's better than nothing. But before submitting, I should really find a stronger test case. I could write one myself by thinking very hard, or I could see if I can find one on the intertubes. I have found one on the intertubes. So this seems pretty good. Let's see if we can just write up this graph. So this is some graph we got from the web. Oh no, is it? It's animated. We can't use this one because they overwrite. Yeah, that was not particularly convenient. I'm looking for one actually that has nodes that are letters. Hey, how about this? All right, this looks pretty good. Don't animate on me. Just sit there. All right, so in this one, S in distance 1 goes to A, S in distance 2 goes to C, C in distance 4 goes to A in distance 6 goes to B. I'm just reading off these edges from the graph. C in distance 3 goes to D, B in distance 1 goes to D, B in distance 2 goes to E, D in distance 1 goes to E. All right, so that's our new web graph. And in the web graph, our target is E. All right, let's see what happens on the web graph. We think the shortest path is A, B, and E, even though we visited D in the interim. A, B, and E. All right. S goes to A, to B, to E. That's a total of, I can't do math, 9. Let's try some other stuff. S goes to C, to D, to E. That's a total of 6. Man, it looks like we're getting the wrong answer. Huh. Dun, 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 something fun to think about. Well, it turns out that we're not necessarily actually getting the wrong answer. We're asking the wrong question. If you take a look at this shortest path, you'll notice it starts at A. I updated the target, but not the source. In this particular example, if you look at it, they start at S. Right? So let's rerun it, now being careful to say, go from start to end. All right, and now they say we say S, C, D, E, S, C, D, E. Oh, this looks much better. 2, 3, 1, it's a total of 6 instead of the 9 that we had before. Yeah, I've gained additional confidence. I could gain even more confidence by destroying some of this input. Like, we needed to go through this C to D edge to make this work out. What if I cut off this C to D edge and try again? I'm going to copy the web graph to web graph number 2. And we had that edge from C to D. This one right here, C to D. And I'm just going to remove it. Now we're going to rerun our Python program on the second web graph. And now it thinks SABE. And because there's no way to get there from C, going down here is just a waste of time. So SABE is correct. BDE would also be correct, but we only need to find a shortest path, not the shortest path. All right, so this seems pretty good. So now I could go back and remove a lot of our debugging output, or at least comment it out before we get ready to submit. And then we would want to format it according to the problem set instructions. Yeah, unreachable. Let's try it one more time to make sure it still works. Oh, we're still printing out something we didn't expect. We're printing out the initial distance map. All right, so now we just print out the shortest path in some Pythonic answer. But for classes like these, we often need to print it out one line at a time. SABE. All right, so tune in next time as we do something similar in OCaml and then something similar in Cool as well.